Uh, Hello, everybody. Today, I would like to present to you some results that we have obtained on the regularity and upper density estimates for the joint law of the stable process and its supremum. This is joint work with Jorge Gonzalez Cazares and Alex Mijatovic from Work University. The main idea is to obtain that the joint law of the stable process and its supremum at a certain fixed time t is infinitely differentiable, and to obtain upper bounds for this joint density. The estimates that we obtain are almost optimal. And we believe they are new in the literature, and actually our method of proof is a method of proof which I think has not been considered so far, which actually comes out from some simulation methods which when applied to the study of these densities, it actually leads to this regularity and upper density estimates. So although our intention is not to carry out simulations, what we are trying to say today is that by studying these simulation methods from a theoretical point of view, you can actually obtain significant results on the density, the existence and the regularity of the density, and upper bounds for them. And actually these upper bounds are almost optimal. So that's something that is, we would say, rare from simulation methods, but in this case, it actually does happen, and we'll try to explain why this is the case. Okay, so let me start with a general, brief introduction of stable processes and its supremum. So a stable process is a Levy process, which, so in general, we'll consider it to start at 0, and is characterized by an index alpha, which is the index of stability. Then the symmetric stable process has a Fourier transform, which is given by this formula, which is up to here in black. But we will consider the case where there is an extra parameter, which is called rho, which is the positivity parameter. So which means that actually when rho is equal to 0, to 1/2, this is going to be the symmetric case, and when rho is different from 1/2, then it's the non-symmetric case, and that non-symmetricity is considered to be the probability of xt being greater or equal to 0, and the range of this parameter is as is given here. Now, our methodology is completely stochastic, but just for those of you who are more at ease with operators and PD theory, let me just say that in the case, for example, when rho is equal to 1/2, then this corresponds to a Markov process whose generator is the so-called fractional Laplacian. And so what we are interested in studying is the joint law of xt and x bar t. So the notation for the supremum is x bar, which are the final, in an interval 0 capital T, the final value of xt, and the value of the supremum in that interval. So clearly, when you say that you are studying the joint law, then you already know that there is a relationship between these two variables. In fact, the supremum has always to be greater than xt, so it means that the density has to be supported in this domain, which is divided by the line y equal to x. And so we would like to study the behavior of this joint density, not only, for example, when x and y are close to 0, or x and y are going to infinity, but also close to the diagonal. So close to the case y equal to x. Okay, so if we discuss this objective from the point of view of PDEs, then we'll have to change a little bit the setting, and we consider the following expectation, where f here is a test function, and the x here indicates that the process xt, the stable process, starts at point x. So this should be a small t here. And so you consider the pair of the Levy process, which starts at x, and the supremum, which is originally perturbed by m. And so you consider this function utxm, and for the Levy measure of, for example, the symmetric case is given by this formula, and therefore you are studying this non-local PDE, where here is the derivative with respect to time, and this is the representation of the fractional Laplacian, which has some extra terms, which are these guys here, which are the effects on the maximum. Okay, so this is not exactly the fractional Laplacian, but is, you could say, a deformation of the fractional Laplacian, because you are considering the pair, the stable process and its supremum. The boundary conditions that are related to this problem are actually these ones here, which you consider some sort of generalized Neumann condition. Okay, because the supremum, we all know, is very much related with reflection, and reflection is related with Neumann conditions. And of course, you have the initial condition, which is what happens when time is equal to 0. Sorry, maybe this 0 should be as lower index here. But anyway, so now I'm going to completely switch into probabilistic mode. So just for people in PDE to know what our result means, essentially we are going to study the fundamental solution of this type of non-local partial differential equations, which are driven by, we'd say, some version of the fractional Laplacian with a certain Neumann type condition. Okay, so now let me discuss a little bit about previous results. So previous results on this problem have actually only been obtained for the marginals. What do I mean by marginals? I mean the most classical results on the stable process xt have been known for a long time. You can probably find them in classical textbooks. And one knows that the behavior when x goes to infinity is of this type. And when x goes to 0 is actually constant in x, but there is a degeneration in time. And there have been many people, and there's a lot of interest on the study of the supremum. Okay. And so we are just to quote one of the ones that we have refer mostly, but there are some other results which have been advanced lately. For example, by Chaumont and Malecki, but we'll discuss this a little bit later. And Donian Savov obtaining the asymptotics of the supremum. And so you see that the asymptotic when when y goes to infinity is actually the same as x, but the behavior at 0 is different. Okay, and of course this is clear. Why? Is because when you have xt's, is a process, a stable process that is supported in the positive and the negative, but x bar is only supported in the positive. So in the results, what we would like to do is not only to obtain these asymptotic properties for the results written in black, but we also want to obtain the results for the derivatives. Sorry, here should be derivative with respect to x. And in the case of a stable loss, this is also well known. You just essentially have to differentiate the optimal behavior here. But for the supremum, this is less well known. There is a final comment on Donian Savov at the end of the paper, which says that probably using similar techniques they can do it, but we believe that these calculations actually quite involved. It means that it demands some calculations, and therefore we are not sure yet that this is the case. But anyway, there is a mention to this in the article of Donian Savov. And as I said at the beginning of the talk, the main arguments that are used in all these techniques are based on stable meanders. So stable meanders means that it's some sort of excursion theory for stable processes, and in particular the Binet-Hopf identity, which actually relates the law of xt, the supremum, and the infimum. So it's very much an analytical method, and what we were trying to do today is actually try to explain to you a method that is actually much more stochastic. Anyway, so the first thing that we need to do now is to try to get a better idea of what could be the optimal estimate for the joint densities. And so, and this is also done in the proofs. Actually, in the proof, we don't study directly the process xt. What we do is we separate the study in these two processes here, which are equivalent, because I'm just taking the difference between the supremum and xt. So this is usually called the reflected process for Levy, and so in the stable case also the same. And actually, for each one of them separately, you can write the asymptotic behavior, and this asymptotic behavior is probably something like this. So this is only a function of x, and this is only a function of z, which is the term of the reflected process. And so what we are going to prove is that this identity is actually true, which means that the optimal bound is going to be almost like if these two processes were independent. Now, of course, then you would ask the question, well, when you transfer this into the pair xt and x bar t, what do you obtain? Well, this is what is going to be written in the next picture. And so in the next picture, what you have is that the density of x and x bar t will be bounded in the optimal scenario by y minus 1, y minus x minus 1 always. This is the density. And these functions f alpha, which appear here. So you have that the space x and y, so this is the axis x, and here the height is y, will be divided in 4 regions. So the region for y is determined by y equal t to the power 1 over alpha, and the region for x is actually divided by this line. So you have these 4 regions. Now, in each region, you see that there is a different sort of asymptotics going on, and you can get these asymptotics up to the diagonal. Okay? Now, what I want to mention here is that there is an article by Chamon and Malecki, which actually mention the asymptotic behavior in this case. Okay, we believe that there is a small typo, and actually in their result they quote like if this t square is t, but we believe that actually it's t square. Anyway, so again, we believe that these results are actually the optimal ones, because also, for example, if you integrate this result at any level, for example, if you integrate the result in this line, which will mean that x is close to 0, or if you integrate this result on this line, meaning that y is close to infinity, then you obtain the optimal results that I just quoted in the previous slide. So you obtain exactly these estimates. Okay, so now, actually, as I said at the beginning, we are going not to obtain optimal results, but actually almost optimal results. What do I mean by almost optimal results? If you see here the appearance of alpha, we will obtain not alpha, but we will obtain alpha prime, which is any value between 0 and alpha. So I cannot take the actual value alpha. Okay, and in that sense, our results are not optimal, are almost optimal. You also see that the fact that you have a non-symmetric parameter rho plays a role within all the estimates, except when you are when both variables are going to infinity. Now, so this is our main result, and let me just show you how we write it. So here it is. And so fxy denotes the joint law of x and x bar t. And we will prove that this distribution function is C infinity in both variables within the domain O. Okay. And of course, outside the domain O, the density is 0. And actually, then you obtain the estimate for all the derivatives. So this looks a little bit long as an equation, but let me just say that, as we explained a moment ago, there is the 4 functions f. The functions f are written with this alpha prime, as I explained a moment ago, which means that the alpha prime is any value up to alpha, and it cannot take the value alpha, which means that this is not the optimal one, but you get a general estimate which includes all the derivatives. Okay, so for example, in the case of the density, you will take n equal to 1, m equal to 1, and then you obtain the y minus 1 here, and the y minus x minus 1, which are the powers that you see in the title of the previous slide. Something that is interesting is that as long as you don't take the derivative with respect to y once only, you will see that there is the appearance of this term 2y minus x, which is related to some sort of reflection principle. Okay, so these are our estimates, which we believe to be almost optimal. And the main reason why we don't achieve optimality is because, as we know, stable processes have the problem of moments. It is well known that if I have a stable process xt and I put it to a power a, then this will be finite if a is strictly smaller than alpha, and it's going to be infinite if a is greater or equal than alpha. So this is the fact that actually create the fact that we don't obtain optimal estimates up to alpha. And so again, this means that when you are doing the proofs for these facts, you have to be very careful about what moments you consider and if those moments are actually finite. Okay, so this is going to be very delicate in the moment of making the proofs. So now let me, before going to the idea of the proof, let me just show you some of the consequences of this result. The first two that I have here, I will not comment too much on them because essentially I'm just taking the marginals. And so one might say that these results were somewhat known before. But anyway, as I said, when you integrate, you obtain the classical results. And for example, here I am quoting to you two different results that are actually obtained due to the estimates for the pair x and x bar. So for example, here you can say that actually when you consider the density, you can understand blow up that happens near the diagonal. And so in some situations, when you consider only the density, there is no blow up, but once you start doing derivatives, then this blow up starts to appear. So the second result, which is very particular to the fact that you have these joint estimates, is that you can try to estimate, for example, the situation here is a situation where you say, what is the probability that if I start at 0, my stable process, that actually I will cross a level y at some point in time up to t, but actually the final value is here. So what is the probability that you will have these jumps and at some point you will go up and then suddenly you will end up in a place far away. And so you see that the result is of this type. And something that is interesting is that the upper bound actually has influence with respect to x depending on how far down you take it. Okay, and these are results that come out from the upper estimates. I will not comment on how to do the proofs of these things, but essentially, once you have upper bound estimates, I think people will understand. The only thing you need to do is to determine the region that you are talking about and doing integrals on these upper bounds. So in that sense, you can use these results in many different situations when you are trying to deal with sets that involve xt and x bar t at the same time. Okay, the method of proof. Now we are going to start discussing the method of proof, and we are going to use what is called the interpolation method, and I will try to explain to you in very simple terms what is the interpolation method. Actually, the interpolation method that we use is extremely simple in its in the idea of how to use it, because interpolation theory is actually a very, very wide subject with many different techniques. But what I'll try to explain here is that we are going to use actually a very basic and simple form of the interpolation argument. Okay, so the general idea, and let me start here, is, as we said, we are going to use some sort of simulation method, which in general means that I have an objective random vector, which in this case I'm writing as f of x. So what I mean here is that x is a process, like the case of the stable process. And then I will build an approximation, which is this fn, which is going to be based on a certain number of random variables. So here, and different ones. And so here I wrote some of them as e, some other ones as g, and some other ones as u, meaning that they are random variables which are IID between themselves, and that the same letter E means that they are copies, but they are independent between themselves, and they might have different laws. And so essentially what I'm going to try to do is I'm going to try to claim at the beginning to say, okay, I know that this sequence of random variables converge to f of x. I know how to study the densities of these finite dimensional random variables, and because I know that, I can obtain properties of the limit random variable, which is f of x. Well, this idea will sound naturally at the beginning, but actually this method is very, very difficult to carry on unless you have certain properties. And here I explain 3 problems. The first problem is that it's very important what is the convergence rate. So the most basic example where this argument fails when you are trying to do these estimates is in the central limit theorem. In the central limit theorem, for example, we all know that you can use binomial random variables to approximate Gaussians, and we all know that Gaussians are extremely smooth, but that these binomial random variables are not smooth. So one of the things that is very important in order to obtain the estimates is the fact of the convergence rate. If the convergence rate is fast, then maybe you can hope to obtain these estimates. If the convergence rate is not so good, like in the case of the binomial approximation, then maybe this is not going to happen. This argument is not going to work. On the other hand, now the second issue is actually an issue that is related with stable random variables. Stable random variables are actually very, very hard to work with because in comparison with the central limit theorem, where you know exactly the laws of the binomial random variables and you know the law of the limit, in the case of stable laws, not even the approximation, not even this star here, not even this approximation will have a clear law. So when I was doing the argument, here the general argument for convergence, I was sort of claiming, yes, I'm using an approximation because I have an approximation. I know how to compute the laws very well. And actually it's not true, because Fn itself will also include some stable random variables, and actually obtaining the laws of Fn in general will be difficult. Instead, what we are going to do is we are going to condition. We are going to condition on these G's and these U's and work only with the E's, because the E's, we believe, explain the main behavior of f of x. Okay? Of course, later I will explain to you what are these G's and what are these U's, but we believe that, so there are some central random variables in the case of the study of the supremum, which actually explain all the behavior. And of course, in that sense, you might also say with full justice that because I am concentrating on the supremum is the reason why this argument works. And that's actually totally true, because these E's, these G's, and these U's will appear as a simulation method for the supremum. Or I should actually say an approximation method for the supremum. All right, so now let's go ahead a little bit more and let's discuss a little bit about the history of these kind of techniques, and also how we plan to deal with this two problems that I just discussed before, the convergence rate and what are these random variables. Okay, I don't want to concentrate too much on history, but let me just quote that some interpolation techniques have already been discussed in the literature in a completely different sense. Of course, these are not related with stables, they are not related with maximums, but they are in a very general framework. For example, Fournier and Printon, they wrote a paper where actually in very, very simple terms, they apply a very simple approximation method to obtain certain results. And later on, Bali and Caramelino, they have generalized this method to a large extent, but now using some sort of interpolation theory technique in order to study densities. But anyway, so far in the articles that I have seen by Bali and Caramelino, I'm not sure that they can obtain optimal estimates like in our case here, and I will explain the reason why. So again, going back to the previous two questions, I need to answer to you these two questions here. The first question was how to choose the approximations, so how to choose the FNs, you remember? And the second question was how to choose the ENs. Okay? And so the main answers for these two questions are, the first one is to use something that is called the convex majorans of Levy processes. The convex majoran of the Levy process, which is something that I will explain next, is an approximation that allows you to have a very simple way to approximate or simulate the supremum and the final value of a stable process. And I will combine this with something that is called the multi-level method, which creates acceleration. But actually, the main point of using convex majorans here, which is maybe the main difference with previous attempts that I have quoted here by Fourier, Printon, and Bali Caramelino, is that these convex majorans actually converge exponentially fast. So the convergence is very fast. While in all the previous results that I have quoted here, the convergence that they usually use is at best polynomial. Now, for the second part, which is how are you going to analyze random variables for which you don't have an explicit law, which is the situation of the stable law? Well, what I'm going to use is something that is called the Chambers-Malo-Stuck decomposition method, which is a method to simulate stable laws. Okay? And in this simulation method, you will see that there are three random variables that would appear in this procedure, which will be E, G, and U. And my claim is that in order to study the supremum, you will need to find in between these three random variables the random variable that is associated with this sort of maximum, and actually what we claim in our procedure is that it is E. Some exponential random variables would actually measure the length of stable increments. And therefore, by conditioning on G and U, you can study the behavior of the maximum, but at the same time of the final value. And this makes the calculations extremely simple. Okay? So these are the two components. And so let me just go ahead and try to start explaining to you what are these convex majorants. Convex majorants have been studied since the 50s, but recently my two co-authors, Jorge and Alex, they have been working on using this as a simulation method. Anyway, so I'll try to explain to you in simpler terms what are convex majorants, and so I will explain them through this picture here. In this picture, in black, you see the simulation of a Levy process. A Levy process which takes its supremum, let's say at this point here on the top, and here at C, this is the final value. Okay? So the idea of convex majorants is to draw the largest linear convex set which covers this Levy path. So you see here it is drawn in red. So this path has a certain number of vertices. So for example, here you see a vertex here. You see maybe another vertex here, another vertex here, another one here, here, and here. Okay? Now, the question is now how to simulate these red lines, because that's everything that you need. You see that actually the lines are increasing continuously until they reach the supremum, and after they reach the supremum, they start to decrease until they reach the final value. So again, we need then to simulate these red lines, and the way of doing it is by selecting first a value u1 here, randomly from the interval 0, 0t. So you take a uniform random variable 0t, and you draw one point, which in this case is this point here, u1. Well, this point u1 will correspond to one of these red segments here. And so this red segment will be determined by two random variables, g1 and d1, and their corresponding heights, which are these two random variables here. So if I can describe the difference cg1 minus cd1, then I will be describing this line. And once I have all these lines, I can easily simulate the maximum, or the supremum and the final value. Because for the supremum, I just need to add all the positive lines. And for the final value, I just need to subtract all the negative lines. And so the good thing about this is that actually cg1 minus cd1 is actually a stable law with parameter d1 minus g1. And so once I have finished this description, I go on to the next one. I take away the interval g1 d1 in the second picture here. I have a remaining interval, and in this remaining interval I draw again another random variable u2, and I repeat the same procedure. I take the interval, I take away this part here, and then I continue. I continue drawing away pieces, and so this is a description of the convex majorant. So once you finish this, you will find the full description of the supremum and the final value. One important note here is that you don't recover the whole path of the Levy process. You are only recovering the supremum and the final value. Okay, so this procedure of taking these uniform intervals, G1, D1, G2, D2, and G3, D3, and so on, is what usually in the literature is called a stick breaking, because you have the biggest stick from 0 to t, you are breaking it because you are taking this piece, then you take the next one, so on and so forth. So the stick breaking process can be described by certain equations, and these are the equations that are written here. But you see here that there are products of uniform random variables, and then the last one, which is the one that I took. I won't discuss too much about the actual equations. You can think about those carefully. But what is really important, and this is with exclamation mark here, is that when you take powers, and here I took the power r over alpha just because they are going to appear later like that, but when you take powers r over alpha, what you obtain are these estimates. So the important part is you see that k is the index of the stick breaking. So how many times you have repeated this procedure. And if you have repeated this procedure, say 100 times, it means that your estimate is to the power minus 100, which means that the size of whatever you have left in this interval 0t is exponentially small. And this is the important point in the convergence. Why does this method converge exponentially? Because when you do this taking uk, gk, dk, when you do the stick breaking, essentially whatever is left is exponentially small. So this will converge very fast. So the way of writing this as an equation again is actually this one here. So you remember I told you have to add only all the positive. So this plus here means positive parts. And they have to be rescaled by the size of the interval. And the size of the interval here is Lk, and is the power 1 over alpha, because that's the rescaling of a stable loss. These SKs are stable with parameter 1, and so this is what is replacing the dk minus gk that I was explaining in the picture above. Okay? Now, again, so you can see again what I was just said a moment ago. These random variables, because of these moment properties, are actually getting smaller exponentially fast. So again, this infinite sum will converge very fast. And as I said before, here you have only the positive parts. So this bracket with plus means positive parts, and that's why in order to make our notation easier later, I'm using the notation x plus. Okay, so I drop the notation x bar and I will start using x plus because capital T is also fixed. And then, as I said before, then in order to obtain the final value of xt, I just need to take away the negative parts. Okay? And so this is the way the approximation method is constructed. And as I claimed before, I hope that you have seen that actually then this converges exponentially fast, as I claimed before. And this is the important point of this approximation method. But still, the second problem that I described before is still here. You still have to tell me how you are going to simulate SKs. I already shown you now these LKs depend on U. So those are the random variables that appear here. And here now I have to explain to you how to simulate stable random variables. And this is the Chambers-Malo-Stuck method. So the Chambers-Malo-Stuck method is a method to simulate stable random variables. And the simulation method essentially is this one here. I hope you can see the green. But actually, it's hard to see because the green is not going to be so important. So these are the GKs. Actually, then the simulation method is composed by a product, EK to the power 1 minus 1 over alpha multiplied by the GKs. The EKs are the exponential random variables, and the GKs are built using this function, which, as you see, have sines and cosines, which we claim to be oscillations. Okay? So what we are going to do is we are going to establish a calculus which is actually based only on this exponential loss. So the only thing that you need to put your interest in is EKs. Of course, you have to be careful about the GKs. For example, the GKs are very important when you are trying to decide if moments are finite or not. So technically speaking, you have to be very careful about the GKs. But again, what determines the almost optimal behavior of the maximum are these EKs. Okay, so now we have our two elements. We have the convex majorant, which are actually going to give us an approximation which converges exponentially fast. And we also have the second component, which is the Chambers-Mallows-Stuck. The problem now is that, of course, this representation here using convex majorants is an infinite sum. So in order to be able to construct something that we can actually, like I said at the beginning, an Fn for which I can do calculus in finite dimensional space, I need to truncate these sums. And so the truncation is done here. I won't spend too much time on this slide because essentially what you do is you cut all the sums up to n. Remember here that I'm going to start using this notation plus and minus from now on. Plus means, if you remember, all the lines that were going up in the concave majorant, and the minus meant all the lines that were going down in the convex majorant. So I will divide the calculation in plus and minuses, so always you will see these plus and minuses in all the equations. And I add this small random variable so that the whole result always has a density. And this now becomes an approximation. And this becomes an approximation because this sum is not going to infinity, it's only up to n. But you see now clearly my structure. This is my Fn in my previous slide. Here are the U's inside the LKs, which makes the thing converge very fast. And EKs, I explicitly wrote them here, which are the exponential random variables, which are going to determine my behavior, density behavior, and these are GKs, which are the oscillations. Of course, we need to do some assumptions about these small errors so that everything works fine. And now you have your approximation. But if you want to use interpolation, you have to use a technique to show how the limit happens. You cannot just write that the limit of the xn's are the random variables that you are interested in. You have to explicitly say how these things approximate. But this is going to come later on. So first, we are going to build an finite dimensional calculus. So it's finite dimensional because I have up to n. Now this part is a little more technical, so I will not explain all the details. I will just say that you need to define derivative operators in finite dimensional space for the plus and the minus, but they are n. So it means that actually all these formulas that come out here, they might look a little bit daunting at the beginning, but actually it's just finite dimensional calculus. And so the first thing that is going to happen is that I'm going to start building integration by parts formulas for the approximation. So here xn, just to recall you, xn has the plus part with n and it has the minus part with n. Okay, so we are approximations of the increasing lines and the approximation for the decreasing lines. And so you could differentiate with respect to the plus or the minus. So this is a function of two variables. And actually then this is an integration by parts formula because here I have derivatives and here I don't have derivatives. So the general idea of how to obtain density estimates is that you will use here, for example, f to be an indicator function. So for example, f of x, y, it will be the indicator of x greater or equal than x0 multiplied by the indicator of y minus y0. So this derivative here will mean density, and here you will have the indicator. Of course, you have to go through approximations, but anyway, I don't want to discuss too much about those technical details. And what you obtain here is you obtain a random variable h&m, which is actually the one that is going to give you all the estimates for the derivatives. So these estimates, actually you have to look at them very carefully. You have the random variables in the denominator. So in the limit, you see that these random variables, will need to be integrable. So you see, one first explosion, you need to have control on the inverse moments, so 1 over x, inverse moments of stable random variables. But also, if you see the formula that appears here, and I have written here in purple, you see that here you have a number of terms. So here m actually is always greater or equal than n, but for the purpose of my explanation, just take m equal to n. And so you see the sum of n exponential random variables minus their mean. And you see that there is no renormalization. So in fact, this term here explodes. When m goes, or n grows larger, this term explodes. So this is something that happens very often when you are using interpolation methods. You have an approximation formula, you are trying to control the density, but the estimates that you have for the density explode. And so the thing that is going to come to your help is the fact that the convergence is fast. So you have to try to balance the fact that you have estimates for the approximative densities which explode. Explode how? Polynomically. And then you also have, on the other hand, convergence. But this convergence is fast. So the way of doing this is what is called the multi-level method, which is nothing else than the usual telescopic formula. It's a way of saying that, for example, the limit of a sequence of numbers an is just the sum from ai plus 1 minus ai from I equals 0 to infinity plus a0. Okay? So it's just this simple formula, which written in a slightly more complex form, it is this one here. So now I have written here in this theorem the general derivatives of order k plus and k minus. So I have many derivatives, and that's why you have, well, these simples here that are a little bit more complex. I won't explain too much about those. And here you have the difference. So these are these differences that I was explaining to you. Instead of starting at a0, I'm starting here at an, but essentially it's the same. So the question, and this is the technical part of the paper, which although I say it's technical because it requires a lot of inequalities, it requires a lot of very delicate estimates, but all of these delicate estimates are algebraic. You have to balance the fact that the convergence of this sequence ak plus 1 minus ak here is geometric. So it's exponentially fast. And on the other hand, you have that these weights here, or these random variables that you have here, they are exploding polynomically. So if you want just to make a very sort of heuristic type of argument, we say that these differences are actually converging exponentially fast. So it's actually something like a minus k. And we are saying that these guys are growing polynomically. So you could say that they are, for example, something like k to the power n. And that's how then this whole thing really converges. And that's how you try to obtain the estimates in that way. And so so that's the idea, but carrying it out is not so simple. As I said, it requires some sort of delicate arguments. And I'm just going to try to explain only a little bit how this is done. So for example, here you have this difference. You sort of try to decompose the difference in such a way that you only have one sequence of h's that explodes, and this other sequence here, which actually is converging polynomically fast. And that's how you carry out the balance. Now, there is a second type of interpolation argument, which I haven't discussed yet, which is also very delicate, and which is the fact now that when you do these differences, you are going to have these random variables here in the denominator. When you take the differences, you are going to have a stable random loss in the numerator with certain powers p. And therefore, you have to be very careful what you do, because you know that when you are going to take limits, moments of stable random variables, and inverse moments too might explode. So you have to use very carefully the inequalities. And just to give you a flavor of what type of inequalities you need to use, for example, you have inequalities like this with the indicator function. And so taking this x piece here will give you some tails. These guys here are the random variables for which you need to find moments, but you need that you understand that you cannot just take any p, because otherwise the moments will explode. And this also explains why our estimates are not optimal, because as I explained before, you are using then the moments of stable random variables, and we know that this one is going to be infinite if p is equal to alpha. Okay? Of course, I can be a little bit more detailed about these sort of inequalities, and these are explained in this slide, but I will not discuss too much about those. So let me just close with some main points of the article. And the main point again is that we have used an approximation method, which is the convex majorans, which converge exponentially fast to the limit. And through the construction of the approximation method, we require the use of 3 different types of random variables, and one of them is the one that determines the supremum. So you have to recognize what is the random variable that actually tells you the actual behavior of the supremum, and in this case is the exponential random variables. And then we do some sort of finite dimensional calculus, which is based on these exponential random variables, and you do integration by parts in order to try to obtain density estimates. These estimates actually explode polynomically fast, and because of this, then you have to use additionally another method which will incorporate in the calculus the fact that the approximations converge exponentially fast. This is done through the multi-level method, which is, as I said before, a very simple type of interpolation technique. And finally, and this is more technical, you have to be very careful when you do all this, because you will always have moments, and these moments, positive and negative, might explode. So you have to do your calculations so that these explosions don't happen. And but other than that, I think the arguments that we are using are extremely simple, although the inequalities that we use might appeal to some people like difficult or not trivial at all. But as I try to explain at the end, these are some sort of also interpolation inequalities where you balance, again, 2 different things. Okay, so finally I will close with some references which maybe are not complete, but also I would like to say that, of course, these might be interpreted as some sort of Malevin calculus, but in the literature, no method as the one that we propose here has appeared. So it's very difficult to say that what we have done is classical Malevin calculus. We believe it is not, and that it is based on certain ideas, on some philosophies that you can find there, but the technique is completely different. Okay, so thank you for your attention, and please contact us if you are interested in any details or if you have any doubts. We are always willing to continue the discussion on this subject. Thank you again.